Welcome to our 10th learning workshop. It says compounds with oxygen. We're actually going to do a little bit of an extension from last week. And last week we talked about alkenes, and we did a little bit of naming and writing of alkenes. But before we leave that off, there's a couple of things that I want to go through with you real quick. First of all is skeletal structures. A lot of times what you'll actually see is not the nice full structures that I showed you in last week's workshop. A lot of times what you'll see is something like this. It'll say name this compound, and it'll be like or something like that. And there might even be like a CL or something. Okay. Well, if you were to try to name this compound, you might be like, well, what the heck is this? Well, this is what's referred to as a skeletal structure. And I want to take just a brief moment to go over this because I realized that I didn't really talk about this last time. In a skeletal structure, none of the bonds to hydrogen are shown, and the carbon atoms are not explicitly shown either. But every corner and every end that's not labeled is a carbon atom. So with a structure like this, for example, there's a carbon atom right here. There's a carbon atom right here. There's one right here. There's one here. There's one right here. There's one right here. There's one right here. And there's one right here. Every corner and every end is a carbon. Other than the one that might have an atom with a Cl labeled at the end of it, like this one up here. The one up here, obviously, there's not a carbon there, it's a chlorine. But the unlabeled ones, those are all carbons. So in something like this, what would the longest carbon chain be? Yeah, it's a hexane. You want to circle that longest carbon chain for me? Because you'll have access to the whiteboard. You can use a different color. I'm going to point. Oh, there you go. Oh, all right, cool. All right. So anything that's not part of the longest carbon chain, of course, is going to be a branch, a substituent. So we have this is a branch, this is a branch, and this is a branch. This one carbon branch on the bottom here, this is going to be a methyl. And this is going to be a methyl. And this is going to be a chloro. So the name of this compound would be what?
2-chloro-dimethylhexane?
Very close. So 2-chloro is correct, but we also need numbers for the methyl groups, right?
Oh,
So
okay.
2-chloro.
2-chloro.
2-chloro. You go ahead.
Oh, 3,4-methylhexane?
3,4-dimethylhexane, but yes.
Oh, okay, dimethyl.
Very good. Very good. Absolutely. That's exactly what it would be. Well done. Okay, so now just want to do one more toss, a little and what would this be?
Alkene.
It is an alkene.
Hexene.
What would it's a hexene. Very good. What's the name? The full name? No idea. That's no problem. Okay, so,
3-hexene?
and that's very close. You're absolutely right that it is 3-hexene, but there's a part of this name that you may not have thought to put because you didn't see it as clearly. Keep in mind that with the skeletal structure, only the carbons are shown, but what else, what bonds are not shown? Bonds to
Hydrogen?
hydrogen, exactly. So in red, I'm going to actually show these little bonds to hydrogen. And I'm not actually going to draw the hydrogens, but so question, if those are my bonds to hydrogen, each of those double bonded carbons has how many hydrogens attached to them?
3.
Directly connected to it. So the carbons that have a double bond, there's two carbons that are double bonded together. How many hydrogens are on each one? In other words, how many hydrogens are on this double bonded carbon?
1.
And how many on this one?
1.
So when each double bonded carbon has exactly one hydrogen, what do we have to do? What do we have to do with the name? It gets a special designation. Do you remember what that is? It's okay if you just say no if you don't. It's cis trans. Cis or trans. So which one would this be?
Would it be a cis?
Yeah, exactly, because in this case the two hydrogens are on the same side.
Cis and trans. I remember
So
it was cis and
you
trans.
gotta watch out for those when you have these double bond compounds. You have to look and see if each double bonded carbon is connected to one hydrogen. If it is, you have to identify it either as cis or trans. Very good. All right, well, let's go ahead and take a look at some different compounds here, or some reactions with alkenes. There's 3 specific reactions of alkenes that I wanted to go over with you. And so I'm going to keep it relatively simple just because I want you to understand it. So the first reaction is what's called hydrogenation. We basically use some sort of a metal, usually like platinum or nickel or palladium, and when we use platinum or nickel or palladium, it causes the hydrogen to add to each of these double bonded carbons. And actually, just for the purposes of clarity, I'm going to go ahead and change the color here. So in a hydrogenation reaction, the double bond is broken down, and instead, each of the double bonded carbons gets a hydrogen. So, oops, forgot to change the colors. So CH3, CH. The double bond is now gone. It still has the same hydrogens it did before, but now it has 2 new hydrogens. One hydrogen from here, and one hydrogen on here. And that comes from the H2. Now, while it is entirely true that I could have simply wrote this as CH3, CH2, CH3. But I wanted to emphasize the fact of where those hydrogens were going. Does that make sense? What do you think? Cool. So this reaction is referred to as hydrogenation. And yeah, so hydrogenation turns an alkene into an alkane. Hydrogenation kind of got a bad rap for a while because of the hydrogenation of fats to make them less reactive and more stable, and in other words, prevent them from spoiling. It also has some unfortunate consequences to the health of those who eat them. All right, so let's go ahead and take a look at our next one, which is halogenation. So in halogenation, we have a similar feature. We get CH3, CH. We'll use the same alkene. And in halogenation, what happens is that the alkene reacts with a halogen. Now it could be either, we'll use Br2 in this case, but it could also be Cl2. It could be F2. It could be I2. But halogenation involves the reaction with a halogen. No catalyst is required, so I don't need the platinum or anything like that. But a similar type of thing happens here. Basically, each of the double bonded carbons gains a bond to bromine. So the product looks like this. The double bond is broken. The only thing that's new is that each of these carbons that used to be double bonded now has a bromine. Okay, so that's halogenation. The second reaction. And then the last reaction that I want to show you with alkenes is called hydration. Hydration. And this is kind of how it sounds. When you're dehydrated, what do you need to do?
Drink water.
Drink water, exactly. So, yes. So, and that means drinking water. So a hydration reaction is the adding of water. So like, for example, I'll start with my same compound that I started with previously. And with my double bond OCH2. And then I'll go ahead and draw my reaction arrow. And we'll react it with water. Here we are. So, what happens is water actually splits up. And it splits up and is going to place an H on one side and an OH on the other side. Similar to the way the others did, but in the case of the others, the hydrogenation and the halogenation, you had the same thing adding on both sides. In hydration, it's not so. You have a hydrogen adding to one side and a halogen or an OH adding to the other side. So how do you know which one to add on which? Well, there's actually a little rule for that, and it's pretty easy to remember. The rule is the rich get richer. You might be like, the rich get richer? What the heck? But that's the rule. The rich get richer.
How does the rich get richer? Now we're lost.
Well, the rich get richer, what that means is that the carbon that is richer in hydrogen will get the hydrogen. And the carbon that is poorer in hydrogen will get the OH. And so I look at these two double bonded carbons here. Which one is richer in hydrogen? Which one has more hydrogen?
H2, the H2,
The
CH2.
CH2. This is the one that gets the hydrogen. The OH is going to go on the poorer one. So I end up with the product of the OH adding here and the H adding here. Of course, like before I mentioned, you could also just write it as, like this. CH3, CH, OH, CH3. But I wrote it like I did so that you could see more clearly where specifically the H and the OH were adding. So this is your hydration reaction. Now in a case where they have the same number of hydrogens, it doesn't matter which one you put where. You could put the OH on one side, you could put the OH on the other side, it doesn't matter. Now we'll say this usually proceeds with a catalyst. And the catalyst is acid, it'll H+. Any questions about these reactions? Do you want to try any of these, or should we just go ahead and move on to the oxygens? I don't expect you'll have too much with this. Oh, practice? Okay. All right, so I'm going to go ahead and clear this board, and I'll draw a couple of practice problems, and I have you guys predict the products. Okay, so let's do this. Okay. And I'm going to be meaning these skeletal formulas. Okay, go ahead and work those out on your own. And when you have an answer, go ahead and hit the little raise hand sign and we'll go over it. You can also give up and we'll go over it together. Let me know with your raise hand sign. Oh, okay. Raise your hand if you're stuck as well. How about you, Carissa? Oh, okay. Well, then, in that case, let's go ahead and go over them. All right, first things first. So keep in mind that just as with before, with these skeletal structures, each one of the ends, each one of the corners is a carbon. All I have to do, all I have to remember is that with halogenation, with bromine, I'm going to add one bromine bond to each of the double bonded carbons, and the double bond goes away. So I will simply redraw the same thing to start, because the skeletal structure does not change, the carbons don't change. I'm just adding a new bond in place of the double bond. So the double bond goes away, and I'm going to add two new bonds. One, each of the double bonded carbons is going to get a bond to bromine. So here's a bond to bromine, and here is a bond to bromine. And that's it. Does that make sense? Any questions? Okay, cool. It's okay if you need to ask questions. All right. So next one is H2O. This one is the tricky one because I have to remember that I'm going to put an H on one side and an OH on the other side. So unlike with the other one, I do actually kind of want to pay attention to how many hydrogens are on each one of these carbons. So first I'm going to mark the carbons. Here's 1, 2, 3, 4, 5, 6. Now using the same principle that I've used before, that carbon always wants 4 bonds. How many hydrogens are on this carbon right here? 1. Yeah, because it always has 3 bonds. 1, 2, or it already has 4 bonds and it already has 3. 1, 2, 3. So it needs one more bond. I'll put an H here. What about this one? How many hydrogens here?
1.
Okay. What about this one?
2.
2. Now, it turns out that none of the rest of these are all that important because remember the H and the OH only add to the most highly substituted, or basically they add to the one, H is going to add to the one that has more hydrogens. But in this case, they have the same amount of hydrogen, right? So it doesn't matter which one you put where. If they have the same number of hydrogens, it doesn't matter which one you put where. So what I will do here is, once again, I know this is an addition reaction. I'm going to lose the double bond. I draw the same skeleton, except that in place of the double bond, where those carbons were double bonded here and here, I'm going to add an H and an OH, and it doesn't matter which one I add where. I'll just go ahead and add the H up here and the OH here, but you could add it the other way and it would be the same compound. It wouldn't make any difference. And that's it. For the last one, all I'm doing is adding hydrogen. So my alkene just turns to an alkane. Since all I'm doing is adding hydrogen anyway, it doesn't really matter. I don't have to show it. If I wanted to show it, I could, but I don't have to. I have a total of 6 carbons here. 1, 2, 3, 4, 5, 6. Basically, the hydrogen's going to add on these two carbons that were double bonded. And like I said, if I wanted to show them, I could just write 1 hydrogen here and 1 hydrogen here. but that you don't actually put bonds to hydrogen in skeletal structures. So I'm actually going to just leave it alone. Make sense? Would you like another shot at it? Want me to give you some different ones?
I'm just wondering why this particular topic is hard. It's difficult. I don't know why it's not just taken.
I mean,
I don't.
it's not too difficult if you see the pattern. But organic chemistry, it is about patterns, and there is some memorization to it. And so the better you are with seeing the patterns, it's going to help.
Do you want to teach us the patterns?
Oh, I just did.
Okay.
In the case of the addition reactions,
Mm-hmm.
the bromine adds to each of the double bonded carbons, and the double bond goes away.
Okay.
And it's the same pattern for each of them. The double bond goes away, and something adds to each side. In the case of bromine, it's a bromine that adds to each side. In the case of hydrogens, hydrogen adds to each side. In the case of water, hydrogen adds to one side, OH adds to the other. But it's always the same thing. The double bond goes away, and something adds to each of the double bonded carbons. Would you like another shot? Would you like some more practice? What do you think?
Yeah.
Yeah? How about the rest of you guys? You want to move on, or do you want maybe another shot at this?
We don't have a hang of this yet.
Okay,
So even if we move on, it's just
that's a good idea. That's a good point. All right, so let me go ahead and give you some more practice. All right, let's do this. All right, go ahead and take a moment and work the problems out, figure out what the products are, and when you're done and you have an answer, just go ahead and raise your hand. All right, so let's go ahead and take a look at it. Uh-oh. And somebody's writing something. Can't quite make out what that something is. No, it's okay. It's hard to write on the whiteboard. So basically, with the first one, did you recognize that you needed to figure out the number of hydrogens on each of the double bonded carbons? How many hydrogens were on carbon number 2? This one.
Yeah, 1.
And how many hydrogens were on the other carbon?
1,
No?
3,
No?
2.
2, yeah. It already has 2 bonds with the double bond, so it has 2 here. 1 here, 1 here. So the rich get richer, right? So which side is going to get the OH? The left side, yeah. The OH is going to come on the side with less hydrogens, and the side with more hydrogens is going to get another hydrogen, and it'll be a CH3. So this will be your answer.
Wow.
Does that make sense?
Would it have been wrong if we put an actual H on the right side?
Yeah, because I did the
Not
same.
wrong per se. It's better, like, so when we're doing skeletal structures, we just don't show hydrogens. So you can put it if you need to for your reference, but in your final answer you should probably remove it.
Okay.
Yes, Daniel, what were you going to say?
Me?
The same as Carissa. I had put the H on in there. So
Okay, yeah, like I said, it's not so much wrong as it is not appropriate to that particular type of representation. So if you need to put it for your reference, that's fine, but I would remove it in the final answer. All right, and then what about Cl2? This one, it's not as hard as you might think. For if we note each one of the carbons, here's 1, 2, 3, 4. Now the double bonded carbons just happen to go up instead of across, but this principle still remains the same. All you have to do is put a chlorine on each of the double bonded carbons. So I could do it like this. I could and I could say, well, there's a chlorine that adds here to this double bonded carbon, and a chlorine that adds here. You could likewise actually bend it the other way if you wanted to, but yeah, you just have to add a chlorine to each of the double bonded carbons. And you don't have to mark the carbons like I'm doing with blue. You don't have to mark the carbons. I'm just doing that so you can see more clearly the carbon structure. Does that make sense?
Yes.
The chlorine is just the same as the bromine. It's a halogen. What about with the last one? What did you do with the last one?
The last one, I think you just draw the shape without the double bond, and then you put the H on both sides.
You're right, except you don't even need to put the H's on both sides.
Right.
Mm-hmm. Okay, yeah, drawing the shape is totally fine. All right. Well, do you want to do it again, or do you want to move on? It's up to you. If you feel like you want to practice a little bit more, I can give you some more practice problems. Otherwise, we can do something else. I need votes. Okay. Good idea. Let's go ahead and move on. If you want to practice with that a little bit more, I do think that there are some more problems in your book that you can practice with. But let's go ahead and move on. I'm actually going to open up, share a file with you, naming and drawing alcohols.
Okay.
Now, this is a cool one because it actually has several different representations, some skeletal structures and some other types of structures, condensed structural formulas, etc. So, first of all, I want to go through naming the alcohols, and then we're going to figure out whether or not an alcohol is primary, secondary, or tertiary. Okay. So, with these skeletal structures, I would strongly recommend maybe making a mark or a little dot for every carbon, just so you don't get lost in the lines. Okay. So the longest carbon chain here for this first compound, number 1, is what?
Four.
Yeah. So that's our longest carbon chain. Yes. In fact, it's all up on our website. I can share it with you as well. Let me actually go ahead and share the direct link to the page where you can download each of those and their answer keys. Here you go. All right, so basically, it's 4 carbons long. Which side am I going to start numbering it from? The left or the right?
The left.
The left. because that's closer to the functional group. And OH is a functional group. So this is 1, 2, 3, and 4. And OH, because it's a functional group, it's going to change the name. It's going to change the ending. So instead of being butane, because 4 carbons would normally be like a bute or butene, for an alcohol, you start with the same root, like butane, but then you end with an OL ending, alcohol, butanol, an OL ending. So you do the same first part of like as if it was an alkane, but you take off the E and add OL. So this is going to be butanol, but I also have to indicate where the OH group is, so I put the number, so it's 2 butanol. 2 butanol. So that's pretty straightforward, similar to what you've done before. But now we have to also check and see if it's primary, secondary, or tertiary. And for this, I want to take a second to describe a couple of different things, or the functional, or the carbon that is bonded to the functional group. In this case, the functional group is the OH. The carbon that is bonded to the functional group typically has a special name. It's typically referred to as the alpha carbon. And I'm going to put a little square around the alpha carbon. Okay? Whether or not an alcohol is primary, secondary, or tertiary is dependent upon how many carbons that the alpha carbon is directly bonded to. So, is the alpha carbon bonded to 1, 2, or 3 other carbons? How many carbons is that alpha carbon directly bonded to? Directly bonded to. Yeah, 2. So it only has 2 direct bonds to other carbons. And because of that, this would be classified as a secondary alcohol. A primary would only have 1 carbon directly bonded to it. A secondary has 2 carbons directly bonded to the alpha carbon. And a tertiary has 3 carbons directly bonded to the alpha carbon. Okay, let's look at the next one. In this case, what's the longest carbon chain? How long is the longest carbon chain?
3?
3. And you could actually do this a number of different ways if you wanted to. You could go straight up. You could go up into the side. You could go down into the side. As long as you do the 3 carbons and this is another thing to note. It's an interesting point that with functional groups, you always have to go with the longest carbon chain that is connected to the functional group. You cannot, even if it otherwise would not be the longest carbon chain, a functional group takes priority, so you always have to go in the direction of the functional group. So in this case, there's a branch in that you have the CH3, and that's on what carbon number? What number carbon is that on? 2, yeah. So for this one, we could simply call this 2-methyl. 2-methyl 2-propanol.
Propanol.
Yep, because it's an alcohol. You might so you would change the ending from propane to propanol. So, what type of alcohol is this? Primary, secondary, or tertiary? Yeah, because if you look at the alpha carbon, which I'll go ahead and put a square around, that alpha carbon is directly connected, directly bonded to three other carbons. So that would be tertiary. Now you'll sometimes see structures that actually have kind of a hybrid configuration in that they'll show terminal CH3s at the end, but otherwise they'll be drawn like a skeletal structure. This is one of those cases. And in case where you get a compound like this, it's very important to go ahead and note where the carbons are, because the carbons that aren't explicitly listed are still present. Now, what's the longest carbon chain for this alcohol on number 3? 4. Well, that's actually not quite right. Yeah, it's going to be 5 actually. So I look at the longest carbon chain, which I'll circle in red. The longest carbon chain is going to be this one. The OH does not count as part of the longest chain. It's just the functional group. And then if I number these, 1, actually I better use blue. 1, 2, 3, 4, and 5. I see that my 2 methyl groups are on carbons 2 and 3. So what would the name of this particular compound be? What would I call this?
Wouldn't that still be 2-methyl-propanol?
Not quite. You only put one of the branches. There's 2 branches here.
Propanol.
We're on 3, not 2. It's not propanol. We're on 3. Anybody else have any ideas?
2-methyl-3-propanol. Oh, what am I doing?
It's actually pentanol. And Frank is right. It's pentanol. You have to give the location of where the alcohol group is, so it's 1 pentanol. And since there's 2 branches, one on carbon number 2, the other on carbon number 3, and they're both methyls, I say 2, 3, 2, 3 dash dimethyl dash 1 dash pentanol. That would be the full name. Does that make sense? You
So
see
can
where
the
I'm getting
result
at?
of 2-methyl-propanol give you propanol? Give you pantanol or what? Sure.
I'm not sure what you're talking about.
For instance, they tell you to make as in, for instance, they say that's 2-methyl-2-propanol. You should get the original alcohol and the result product, the product, right, that it creates with that. How would you do that kind of an equation?
It depends on what type of reaction you're talking about. We're not really dealing with reactions yet.
Okay. Because why I'm asking is because in our lab, and they gave us the 2-methyl-2-propanol, right? And they say write the original alcohol, and then the products that will be created from that.
And once again, that depends on what type of reaction and what type of reagents you're using um, in order to determine that, because that question in the context of this structure, this substance doesn't actually make any sense. So I'd have to look at that a little bit more closely.
That's what they gave us. They gave that to us, and they say you should write it out.
I think you might be misinterpreting it, but I'll have to take a look at that later. Um,
The question. I'm not looking for it.
all right, but what about structure number 3? Does that make sense how you name that?
2, 3 metal, 1
Trisha, Leanne, do you follow that? Does that make sense? Okay. Now, what type of alcohol is that? Primary, secondary, or tertiary? What type of alcohol is that? Primary, secondary, or tertiary? Okay, so once again, let's look at the alpha carbon. That's the carbon that's directly connected to the functional group. Yeah, the alpha carbon is only directly connected to one other carbon. And so therefore, this would be primary. I like that.
Did you teach us how to identify primary, secondary, and tertiary?
Yeah, I basically said that you look for the carbon that's directly connected to the alcohol, or directly connected to the functional group, because it's a more generic designation, but look for the carbon that's directly connected to the functional group, specifically the alcohol. If that carbon, which is called the alpha carbon, if that carbon is bonded to one other carbon, it's primary. If it's bonded directly to 2 other carbons, it's secondary. And if it's bonded directly to 3 other carbons, it's tertiary. So I'd like you to go ahead and try your hand at naming number 4. Try your hand at naming number 4 and determining if it's primary, secondary, or tertiary. And when you think you have an answer, or if you give up, just raise your hand. Okay?
Can I try whether it's 2-chloro, 2-methyl, 2-propanol?
Could you repeat your question?
No, I said, is it 2-chloro, 2-methyl, 2-propanol?
No, not quite. Okay, you said you think you have an answer, Leanne? Let's give it a try. So the longest carbon chain is how many carbons long? That will tell you if you're on the right 4. Very good. Probably this one, although you could actually choose other paths that would be identical. So you're right, it is butanol. Now, which side would you start numbering from? Frank got it. It's the right side. Because you always have to ask yourself which side is closer to the functional group. And this is why it's sometimes important to mark those carbons here in the middle and the one here. The side that's closer to the functional group is the side with the chlorine. You always have to start from an end carbon too. I can't start numbering in the middle. So either this carbon has to be 1 or this carbon has to be 1, but the one with the chlorine is closer to the OH. So I start from that side. So what did you come up with a name then? And you can speak it or type it.
1-chlorobutanol?
That's closer, but you forgot the methyl branches. And
Oh, okay.
you also forgot to give the location of the alcohol group.
Oh, okay, cool.
Anybody else want to try to finish?
Is it 1-chloro-3-dimethyl-2-butanol?
Very close. The only thing you are missing is the extra 3, because you have to give a number to each methyl group. So it's 1-chloro-3,3-dimethyl-2-butanol. Everything you said was right. You just said 1, 3 instead of 2. Very good. It takes some practice. It definitely does, but you are getting the hang of it. Now, what type of alcohol is this? Is it primary, secondary, or tertiary? Very good. It is secondary. Is there anyone who's having trouble seeing why it's secondary? I can explain it if you need me to. It basically, you got your alpha carbon here, the one that's attached to the OH, and it's directly connected to 2 other carbons, the one with the chlorine and the one over here. That's why it's secondary. All right, very good. Now, I do want to do number 5 with you, because number 5 is an interesting one. Basically, when you have alternating double and single bonds in a ring like that, it's actually called a benzene. It's called benzene. It's a very special and very stable organic molecule. So anytime you have a 6-membered ring that looks like kind of like cyclohexane, except it has alternating double and single bonds, that means it's an aromatic ring called benzene. Now, when benzene is attached to certain other functional groups, it gets special names. It gets different names. And the name of benzene when it's attached to an alcohol is phenol. So essentially, well, let me get rid of that. That's terrible. So when benzene is attached to the alcohol, we call that phenol. Phenol.
Yeah, phenol.
I'll put PHENOL. Phenol. Okay. And the number 1 carbon is always, always, always the one in a cyclic compound. The number 1 carbon is always the one that has the functional group on it. So if I was to mark the individual carbons with blue here, at least I think that's blue. I am colorblind. So I'm not totally sure. But yeah, so the number 1 carbon would have to be this carbon right here. Okay, thank you. But yeah, so that'll be number 1. So then I only really have 2 choices as far as numbering here. I can either number clockwise or counterclockwise. Which way should I go?
Clockwise.
Yeah, clockwise in this case, because that'll give you lower numbers, right? If I go the other way, it'll be on 4 and 5. If I go this way, it'll be on, the branches will be on carbons 3 and 4. So that'll be lower numbers. That's the second level of priority. You remember your levels of priority? Functional group, lowest numbers, alphabetical order. So we have a 2-carbon branch here, and we have a bromine branch here. So, oh, by the way, with cyclic compounds, I don't need to put a number for the alcohol because the functional group is always automatically on the number 1 carbon, and so it's automatically understood that it would be on number 1, and therefore you don't need to put a number. But I do have to indicate the location of the rest of the functional groups. So how would I name this? How would I name the rest of this?
Like 4-bromo 3-methyl phenol.
Very close. You said 4-bromo-3-methyl, but that's a 2-carbon branch, so it should be 4-bromo-3. What's a 2-carbon branch called?
Ethyl.
Exactly. Yeah. So it should be 4-bromo-3-ethyl phenol. And that would kind of, one could try to call that a secondary alcohol. Typically, we don't really talk about the, it's not strictly speaking a secondary alcohol because whenever it's bonded to a aromatic ring, a phenol actually behaves differently than a secondary alcohol.
Dude,
So
this is
we
awesome,
kind of
man.
just call it phenol. All right. So now all we have to do, so we don't have to worry about the primary, secondary, tertiary designation there. And there's one more thing I want to do with the naming before we move on a little bit, and that is with thiols. Now, thiol is basically, it's the same thing as an alcohol. You do the same type of stuff, except the ending is a little bit different, okay? You just, with thiols, you strap on the number and the word thiol at the end, but otherwise you name it like you would an alkane. So it is a functional group, but it has, the naming is a little bit different. So
What have you got on the alerts page and the trends page?
okay, so we're going to go ahead and number, or we're going to go ahead and mark our carbons here.
Got it. And do you have on the computer? You have
We're
something
going to go ahead and
Please, can you take down your microphone if you?
I already took care of it. Sorry. I just went ahead and we'll go ahead and circle the longest carbon chain here for the thiol, and it happens to be 4. I'm going to start numbering from the side closest to the functional group, so closest to the SH. That'll be 1, 2, 3, 4. And there's a methyl group, and then there's the thiol. So, like naming in previous times, we're going to go ahead and start with our substituents. It's going to be 2,2-methyl. But then we're going to do something interesting. We're going to actually say, well, there's actually 2 ways that we can do this. We can either do it like this. We can either say 2-butane thiol or 2-methyl butane dash 2-thiol, both of which are completely acceptable. either 2-methyl-2-butane-thiol or 2-methyl-butane-2-thiol. Now I'm going to go ahead and give you a chance to name number 7 real quick. And once you have an answer, go ahead and raise your hand. It's very close. You're missing a substituent. Uh-huh. Did anybody else get the whole name? What would this be called? There you go. Yeah, 3-methyl-2-butane-thiol. That is correct. 3-methyl-2-butane-thiol. Very good. Now I do want to have you guys draw some of these because I do think it's helpful. Go ahead, and drawing is always easier than naming because with drawing you can control the numbering and then add on the groups from there. Drawing, you always start with the root name. Go ahead and draw number 2. Your root name is cyclopentanol. So cyclopentanol, I'll actually go through this one with you and I'll have you guys do a different one. Cyclopentanol is a 5-carbon chain and it's a cyclic, so it goes in a ring like this. Now, when you have an alcohol that's a cyclic alcohol, number 1 automatically is your alcohol group. So I'll put the alcohol on this carbon, and I'm going to call this carbon number 1 because I can choose to make any carbon I want number 1. And then from there, I can go ahead and say, well, this will be 2, this will be 3, this will be 4, and this will be 5. And then if it says 3-chloro, well, now that I have it numbered, all I have to do is put a chloro group on carbon number 3. And there you go, I'm done. Try drawing a structure for problem number 3. Problem number 3, try drawing a structure for problem number 3. And when you have an answer, go ahead and raise your hand.
Okay, I have to say this is hard for me. I write left-handed and I'm trying to write with my right hand on a mouse. Okay, so
that's okay.
It's
It's not pretty, but it's accurate so far.
okay.
There's just one other methyl group you got to put in, right?
Yeah. Okay. Just want to let you know. Thanks.
I'm a lefty too, so I feel your pain. Although interestingly enough, I think I might be ambidextrous.
Okay, so I put my alcohol here. This here is a CH3. This is a CH3. This is a CH3.
Mm-hmm.
Does that make sense?
No, very good. That's exactly correct.
Okay. So and then I have 1, 2, 3, 4, 5, 6. So that's the hexanol. And then my alcohol's on the 1, so that's the 1-hexanol. So I have 1, yes, and there's 2, 2, 3, yeah. So I think.
Now, the only the way that I drew it up there, it would be considered more standard, but what you drew is technically speaking correct.
Okay.
So, just in case if others are kind of wondering what you were drawing, yeah, I have a lot more experience drawing on a mouse. Okay, cool. Very good. Very good. That's awesome, though. You totally nailed it. Well, I would encourage you to practice, all to practice a little bit more with this naming and the writing of the alcohols. There is more practice available up on the website, I think, maybe. If not, there's definitely some in your books. These ones down here, these are kind of challenge problems. And so definitely I would say, yeah, go ahead and do it. So draw the structures which are incorrectly named and give the correct name of the compound. So the name will allow you to draw the correct structure, but that's not how it should be named. And so that's why I say draw the name of, or draw the compound and then properly name it. So this will be a really good practice for you. We didn't quite get to reactions with alcohols, unfortunately, but we'll tackle that next time on our upcoming Tuesday session. There'll be compounds with oxygen part 2, and we'll dive into ethers, and we'll also get into reactions with alcohols, and we'll also get into ketones and things like that, ethers, and ketones and aldehydes. Well, cool. It's been fun. I hope this was helpful, and I will look forward to seeing y'all next week. Thank you for coming.